All right, let's look at the repeated quadratic factor number 2. Inverse Laplace transform of 1 over quantity s squared plus k squared squared is equal to 1 over 2k cubed times quantity sine of kt minus kt cosine of kt. Right? So the proof is actually a homework. But I'll get you guys started. All right? So here, first thing is I'm going to let just like the first one, we're going to call f of t t cosine of kt. Right? Then we're going to take a couple of derivatives again. So f prime of t using product rule. So 1 times cosine of kt minus t. The reason is minus is cosine of kt, derivative is k times sine of kt. Right? Then we take the next derivative, so f double prime of t is equal to negative k sine of kt. And then here's product rule, so derivative of the negative kt is negative k sine of kt. Negative kt times derivative of sine of kt is k, so k squared, cosine of kt. So if you clean it up, you're going to get negative 2k sine of kt by combining the first two terms minus k squared t cosine of kt. Right? Then we take the Laplace transform of both sides of this equation here. So you take the Laplace transform. Right? So you have, since it's a second derivative, s squared capital F of s minus s times f of 0 minus f prime of 0 is equal to, here's a negative 2k, just a number, right? Then Laplace transform of sine of kt is k over s squared plus k squared. And there's a minus k squared. And since t cosine of kt is the same thing as f of t, so Laplace transform is f of s, capital F of s. Right? Then we can find f of 0 from here. If you plug in 0 for t, 0 times anything is going to be 0. And this one we have to be a little bit careful. What would be f prime of 0? Right? And a cosine of 0 is actually 1. Then 0 times anything is 0. So it's 1. So we have f of 0 is 0. So we can scratch this one out. But here we cannot scratch this one out because this is going to be just 1. All right. So we have, we're going to get, if you clean it up, you have s squared capital F's of s, and here's a minus 1 is equal to negative 2k squared over s squared plus k squared minus k squared F's of s. Right? And remember that F's of s is just a Laplace transform of f, so we can rewrite it as actually I'm going to do a little bit more. I'm going to move this guy over to the other side, right? So we're going to get here. So you have s squared plus k squared, and then you have capital F of s is equal to, right? Then I'm going to move this negative 1 over to the other side, so it becomes positive 1, right? Then you have a minus, so this was already there, 2k squared over s squared plus k squared, right? Then we can just divide it through by s squared plus k squared. So you have f of s is equal to 1 over s squared plus k squared minus 2k squared over quantity s squared plus k squared squared, right? Then remember that the capital F of s is simply Laplace transform of t cosine of kt, and then right hand side is 1 over s squared plus k squared minus 2k squared over s squared plus k squared squared, right? And if you take the inverse Laplace transform, you will see that t cosine of kt is equal to, this is going to be 1 over k sine of kt. And then this is going to be, I'm going to just write it this way, negative 2k squared. Pull that out. Then you have an inverse Laplace transform of 1 over quantity s squared plus k squared squared, right? So I did was just pull, this is just a constant, pull it outside here and take the inverse Laplace transform of the rest of it. But to remember that what you're looking for is this guy, right? So all you have to do is solve for that. So I'm going to let you guys finish it. All right, that's it. I hope that this was clear.